Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell. What we're doing is back to the basics. What we're going to do this time is long division algorithm for integers and polynomials. So this lecture specifically what we're going to do is do the division algorithm, is what we call it, for the integers and how to do this kind of business or this kind of business. And then we'll do the analogy to polynomials, and then we'll give examples of the both processes. Let's do that. Okay, for the integer version, the division algorithm for positive integers, you can do for negatives, but I'll get you with negatives in another video. Let a and b be positive integers. You can't divide by 0 either. We'll also explain why that's true, because I told you lightning might try and get you, so don't do it. Right now, we'll make sure that they're both positive integers. Then there exists unique, so this is an existence and uniqueness theorem. There exists and there's no more than one. So there are unique integers q called the quotient, and this is where the uniqueness comes in, this restriction. A remainder r, which is either 0 or less than or equal to b minus 1, but strictly less than b. So if you want to change that, that's also an equivalent statement. It's either 0 or strictly less than b, so this will be proper when we do the rationality of the ratio of them. So we have two positive integers a and b. There are two more unique integers q and r, such that this is true. Or what does this also do for us? If I'm dividing b into a, this says that a over b will equal qb plus r over b. And then I can distribute this into both of these. So this would be qb over b plus r over b. Cancel, cancel. And this tells us that a over b can be written as a whole integer q. It's an integer q plus a proper ratio of two integers. And so this is how we use the division algorithm for integers to write this guy as mixed radical or mixed fractions, which I don't particularly like, but they will write this as q times rb. But what, and then they're like, you multiply, no, it's a sum. It's a sum. This is how we do that. Let's do an example, and then we'll do the polynomial version. All right, example 1. Find the quotient q and the remainder r when 37 is divided by 4. In here, I usually fix this as the big one is a and the little one is b. So a is 37 and b is 4. Or you divide 4 into 37 and find the quotient and remainder, and then we can write it as a mixed fraction if you want as well. What do I do with that? Also, if you didn't like long division, let's do the crash course in our notation and how we set this up. And I'll give you the algorithm on how to systematically find the quotient and remainder. But I'll also point out something that if you didn't like the game originally, we're going to say, how many times does 4 go into 37 without going over? And especially if you had a really long number and you really have to keep doing it over and over again, what's going to happen? We'll do that next in example 2. List the multiples of 4 first, and that game will be much easier. What do I mean by that? We are dividing 4 into 37. There's the way that I write this. There's slightly different versions of how to set this up. That says I'm dividing 4 into 37. The quotient will appear here, and the remainder will appear here. And we know that the remainder is either 0, 1, 2, or 3, because it has to be an integer, which is either 0 or strictly less than 4. So the remainder possibilities are 0, 1, 2, and 3. We're trying to find out which one that is, and then what the quotient is. As we do that also, you want to do, this is how we do this on an exam, 4 and then 4. 4 plus 4 is 8. And then do another 4. 4 plus 8 is 12. I'm sure you can list the multiples of 4, but then another 4. If the numbers are bigger, that's how you do that. 16. And then you keep going, and then this is times 1, times 2, times 3, times 4. And then what are we going to get? 420 times 5. Now I have to list them backwards. But now what are we going to get? 24, 28, 32, 36. Why am I doing this? You're like, oh, this takes such a long time. I know, but then if you have a really big number, that'll speed the rest of the long division process up drastically. Now what am I going to get? This is 6 times 7 times 8 times 9. Now that I have that, I ask myself, what's the closest multiple of 4 that goes into 37 without going over 37? It's like, oh, there it is, 9. And then I have the answer. And then so what do? We put the 9 here. We write 36 below. And we subtract, which gives me a 1. Because 1 is less than 4, we can stop. And what that tells me is the quotient q is 9. the remainder r is 1, which had to be one of those guys. And this tells me that 37 is equal to 9 groups of 4 plus a remainder of 1. And if I want to divide 4 into that and see what the fraction is, that says where does 37 over 4 lie on the real number line? Which two integers is it between? Oh, now this tells me that 37 over 4 is equal to 9 plus 1/4. So I even know the decimal of that, 9.25 if you want the other avatar. So it has to be between 9 and 10. This is how I can gauge where they are in the other applications of that. Let's do one now where I'll use 4 to keep this so I don't have to erase these guys, but let's make this guy a much bigger number. All right, example 2, we've changed a from 37 to, well, how big is he even? 1,237,589, some big integer. Now I have to divide 4 into that. And now you'll see, especially if, what if 4 is 17? What are the multiples of 17? 17, 34, I don't know. So I'll list them out and then you'll play the game a whole lot better. 1, 2, 3, 7, 5, 8, 9 is being divided by 4. Where what two integers is 1, 2, 3, 7, 5, 8, 9 over 4 between? We're about to find out, but I need the quotient and the proper rational ratio. So how many times does 4 go into 1 technically? They say you don't need it because zeros in the front of our decimal expansion don't add. That's 0 times that power of 10. But 0 times technically is there. And so what are you supposed to do? 4 times 0 is 0. You subtract, you bring it down, you get a 1. They say you don't have to start with that process, but technically that's the algorithm. Now what do? I bring the next number down. They say you can start by just finding the first integer, which 4 actually does divide into, and then start from there. But you don't really need to. Add the 0 guy, he's good. He was the epiphany in our whole expansion anyways. Now 12. 4 goes into 12 3 times exactly. So I get a 3. And then I get a 12 exactly, and I get a minus. So I get 0. I bring the next number down. And then now you see why I need it, so I might as well done it the first time. This 0 I don't technically need anymore, but the one in between here I will, and then don't forget it. 4 goes into 3 no times. And I subtract and I get 3. Now I bring the next number down, and there's our friend 37, which we know is 9. So I get 9. I already have the outcome 36. I don't have to think anymore as I'm doing the algorithm. It's right there, 36. I subtract. I get a 1. I bring the 5 down, 15. How many? Oh, 4 is too much. It has to be this guy. Another 3. And I get 12. And you'll always realize, start at the top of your page because it's going to go down. What's the stairway to? Nowhere near hell, but we'll make it a much bigger number and then we'll get close. You'll not like this process eventually. 3. And then I bring, who was I bringing down? The 8 now. Oh, 38. 36. So we're going to get another 9. If you don't, there you bring it up 2, and then I'm bringing the 9 down. 29. Oh, 7. And I didn't even cook it up with the same remainder. I got a remainder of 1. How do I know that's less than 4? So I can stop. That now tells me that 1, 2, 3, 7, 5, 8, 9 is equal to 309397 times 4 plus 1. And so where is it between? It's between this integer and this integer plus 1 with the 9, 8 on there. But this is how we do long division and write even if it's an improper division where the number on the top is much bigger than the number on the bottom. I have to erase a little bit. 1, 2, 3, 7, 5, 8, 9 over 4. Who's that guy equal to now? That's equal to 309397 plus 1/4, 4.25. This is fairly useful. And we now have a complete analogy, which is slightly different. There's a couple of nuances. They're polynomials. They're a big mathematical, they're a larger mathematical beast than just the integers, but it's a new mathematical object. And we want to say, can we run the algorithm on those guys? Can I divide a polynomial into another polynomial like I did integers? Yes, you can. And the algorithm's awfully similar, but slightly different. The degree of the remainder now has to be strictly less than the degree of the divisor polynomial. What? do that. All right, the division algorithm for polynomials. Let a of x and b of x be degree n and m polynomials respectively. What does that mean? Crash course in that means that the highest power positive, or the highest integer power of x appearing is n, and that means also that that an, that coefficient would be non-zero, and the highest power in b would be of x will be m. If I have that, then we have a completely analogous version of the division algorithm for the integers. For the polynomials, there have to be unique polynomials q of x and r of x with now the degree. Also, this is our notation for degree, so we don't have to write it down every time. But the degree of r has to be strictly less than the degree of b. And then you can watch the next videos if you want to see where this goes. But if we have rational functions, or we want to do partial fraction decompositions, etc., what we want to do with that is we always want to have a proper rational function. We say it's proper if the degree of the polynomial on the top is strictly less than the bottom. But if we don't have that, and I always start assuming that this guy's degree is larger than b of x, I'm going to divide the little polynomial into the bigger polynomial to find out if it has factors or not, or find the quotient remainder. Once I do that, we can write just like the integers. All we did was right now is put the of x's, and it's the exact same statement, where now here the key restriction is the degree is strictly less. But that says that these would be proper if I took ratios of those, and that's exactly what happens. So now if I have an improper rational function, I can use the division algorithm to write it as a polynomial plus an improper rational function. And then what the heck would we want to do with that? Well, we'll see in a second. First of all, let's do an example of how to do this with polynomials. All right, this time what we're going to do is we'll set everything up the same way. We're dividing, find the quotient remainder when b divides a. So we're dividing b into a. So we write b of x on the outside just like if it was the integer 4. And we write the a on the inside, just like it was that horrible integer, x to the 5 minus 9x to the 4, plus we want to make sure that we don't, so I'm going to put 0 coefficients even if they're in there. So there's no cube and there's no x term, but I'm going to put those in so that everything lines up just in case, so that I don't have problems with this. So what I'm going to write is 0 times x cubed plus 3x squared plus 0 times x minus 3. So that's one of the good tips. Either you have to pay attention and make sure everything lines up, or just put those in, the 0 terms in there, and then when I start dividing this guy into this, everything should work out. Now I ask myself, and I don't have to list multiples anymore, I ask myself, what do I have to multiply this leading term by to get this leading term? And it looks like a 9 for the 27. And an x cubed to get to x to the 5. I'm assuming we know the exponent law, that this is multiplication in the base is adding in the exponents. So I can write that as 2 plus 3, which is x to the 5. That's how I get that term. The quotient will be slightly different each time we do this step, and we do the subtraction and then restart. We get a plus in between each of the terms, and this is how we're going to form the quotient and then eventually the remainder. How do we know when we stop? When we get, in this case, a linear polynomial, because the degree has to be less than this guy. So if it's quadratic or higher, we have to keep going. As soon as it turns linear, we can stop, and we've got a remainder, which will either be 0 or degree 0 or degree 1. The 0 polynomial is degree 0. So what do I do with that? I now multiply this. I said it with saying, to get the 5, we multiply by x to the 3. And then to get the 5, we multiply by 3. Now what I do with that, I multiply this by this. So I'm actually doing 9x cubed times 3x squared minus 3x plus 1. And then I'm writing it below, and that's why I put the zeros in, because I am going to get an x cubed term. But if I didn't put the 0, it'd be like, who am I subtracting? Yeah, line everything up and add the zeros, even if the polynomial doesn't have those coefficients in there. So what am I going to get? Exactly what I wanted, 27x to the 5. That's when we subtract, that one will disappear and we can keep going. Then what am I going to get? I'm going to get minus 27 x to the 4, and then plus 9x cubed. And because I wrote the 0, everything lines up. Now I draw this, I put brackets because it's a polynomial, and I subtract. These cancel. Negative 9x plus 27 is 18x to the 4. And then 0 minus 9 is negative 9x cubed. Now bring the rest down. Minus 3. Don't change it. Now what are we doing? Oh, math isn't surgical. Erase that one. We're going to do it again. Now what do I multiply this by to get 18x to the 4? What's it going to be? 6 is the number I need. And then what's the power of, I need x squared. So now what I do is 6x squared is going to be multiplied by 3x squared minus 3x plus 1. When I do that, what do I get? 18x to the 4, which is what I wanted, so it will cancel. And then I'm going to get, same thing, minus 18x cubed and plus 6x squared. And then I draw my line. I ask myself, what am I doing? Subtraction is the binary operation I'm doing. And then I carry it out. Minus minus will go away. 9 minus minus 18 is positive 9x cubed. 3 minus 6 is minus 3x squared. Bring everything else down. Does this actually divide into it? I don't know. I just picked it out of a random book. I mean, I made this up because I'm a wizard. Now what do? I do the same thing. I regroup. What do I multiply this by to get this by to get this? It'll be plus 3x, it looks like. Can I stop? Not yet, because I have degree 3, which is larger than degree 2. Keep going. Now I'm going to multiply by 3x. What do I get? 9x cubed minus 9x squared plus 3x, and ooh, luckily it lined up again because I wrote my zeros in there. I subtract, I put brackets, minus minus. Negative 3 minus minus 9 is 6x squared minus 3x, and then bring the rest down. Can I stop? No, this is degree 2, and so is that. I have to keep going. My final step will be, what do I multiply this by to get that? A 2. And so what am I going to get? Let's move this up the same way we would. We have 6x squared minus 3x minus 3. If I multiply that, what am I going to get? I was doing it in my head, go slow. I was multiplying this by 2. So 6x squared minus 6x plus 2. Then I'm going to subtract those, put brackets, cancel, cancel. It didn't divide. Okay, good. So 3 minus minus 6 is 3x. Negative 3 minus 2 is negative 5. So what does that say? That says, can I stop? Yes, because this is degree 1 and this is degree 2. Therefore, what that says is, with those two polynomials now, this says this horrible beast, 27x to the 5 minus 9x to the 4 plus 3x squared minus 3 is equal to 9x cubed plus 6x squared plus 3x plus 2 times 3x squared minus 3x plus 1 plus 3x minus 5, the remainder. This is a of x equals q of x times b of x plus r of x, where the remainder now has to be strictly less than my divisor. And so if I write this as the ratio of polynomials, 3x squared minus 3x plus 1, this now disappears. Minus 3x plus 1. I now get an improper rational function becomes a polynomial plus a proper rational function. When would I do that? Let's do one more example and I'll show you. All right, so now say I have some other, you can watch another video about partial fraction decomposition if you want. It'll be in the link below or something like that. I don't know how any of this works. Push buttons, looks down there, read something. We have videos on partial fraction decomposition. So we force feed you how to do long division of polynomials, and we show cleverly that it's analogous to doing long division of integers, which hopefully you learned when you were knee-high to a grasshopper in grade school. And now it's like, oh, it wasn't too much more sophisticated, just polynomials instead of integers. Why would I want it though? One way that we can use it is, say I want to integrate this horrible thing. If you don't know what integral calculus is, then start learning integral calculus, and then I'll see you in a few years when we do that, and we'll revisit integration techniques. But when we're doing integrals, one of the techniques is called partial fraction decomposition, which must be carried out on proper rational functions. This is not proper, degree 3, degree 2. What am I going to do with that, therefore? I'm going to use long division of polynomials quickly, and then use, if after I do that, you can turn off the video or ignore it entirely, or go watch the card on partial fraction decomposition. I will quickly then show you that this turns into the power rule and arctangent function. What? First, do the long division. I have x cubed plus x plus 1 and x squared plus 1. And I didn't write the 0 terms, and you said I should. I know, but I've already seen how this works out, and everything will line up anyways. What do I have to multiply x squared by to get x cubed? X. When I do that, I'm going to get x cubed plus x. Oh, everything lined up. Minus, cancel, 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 cancel. 1, can I stop? Yes, a degree 0 polynomial is less than a degree 2 polynomial. What does that say? In one clever quick step, this improper, or x cubed plus x plus 1 is equal to x times x squared plus 1 plus 1. Why do I want that? Because that now says that x cubed plus x plus 1 over x squared plus 1 is equal to the polynomial x plus 1 over x squared plus 1. And then the integral of a rational function becomes a transcendental function, arctangent. What? Now the integral of this is where you stop and you can switch to the next video of mine. The integral of x cubed plus x plus 1 over x squared plus 1 dx is equal to now the integral of x dx, which is the power rule if you know what we're talking about. That's the easiest one you're going to get ever, plus the integral of 1 over x squared plus 1 dx. And we show using implicit differentiation that the derivative of arctangent is 1 over x squared plus 1, so the integral of this is arctangent. So this is 1/2 x squared plus arctan x plus a constant of integration. Blah, 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 blah. Polynomial long division, first of all. Please subscribe right here. I'll see you next time.